Welcome to The Explainer. Today, we are going to cut right through all the hype around Retrieval Augmented Generation, or RAG. Let's just forget the buzzwords for a minute. What we're going to do here is build a real, practical, step-by-step guide for actually making your AI search systems better. And we're basing it on what engineers at places like Google are doing in the real world. Okay, let's kick things off with the single most important idea for our entire journey today. This quote from David Karam at PyLabs, it just nails it. The goal is not to go out and use the fanciest, shiniest new technique you saw on Twitter. Nope. The goal is to apply the right technique, and only when you actually have a problem that needs fixing. So be pragmatic, be targeted, and put your energy where it's actually going to make a difference. So here's our roadmap. We're going to start with the most critical piece, the right mindset. Then we'll build up our technical toolkit, looking at retrieval first and then ranking. And we'll wrap it all up by tackling those really tricky system-level problems that always pop up once you've gotten the basics down. Right, so before we touch a single line of code, before we even talk about a single algorithm, we have to get our process right. We have to adopt a system for improving things. This is what engineers at Google call the quality engineering loop. And honestly, it's the foundation for everything else we're going to talk about. This loop right here, this is where you're going to live. First, you baseline. Just build the dumbest, simplest version of your system and see how well it does. Second, you do a loss analysis. And I don't mean looking at some fancy aggregate score. I mean you dig in and look at the specific queries where your system failed. And only then, once you know what's broken, do you do step 3. Reach into your toolkit and apply a very targeted fix for that very specific problem. You got to start with the problem, not the solution. Okay, let's dive into the first part of our actual toolkit, retrieval. This is all about one thing, getting the right documents out of your knowledge base to begin with. Because let's be real, if you don't retrieve the right information, the best, most powerful language model in the world can't save you. You should always start here if you can. I mean, if you've only got a handful of documents, why overcomplicate it? Just stuff everything into the model's context window. It's the do I even need RAG step. But you're going to hit a wall with this approach pretty fast, as soon as your document collection gets too big or your texts get too long. So, what happens when your documents don't fit in the context window anymore? Well, you pull out a classic tool, keyword search. This is the absolute workhorse of search. It's been powering systems for decades with algorithms like BM25. It's super fast, easy to set up, and it's fantastic at matching specific terms. But it has a very, very clear weakness. And this slide just lays it out perfectly. If your user types iPhone battery life, keyword search is your best friend. It finds those exact words. But what if they ask a question like a normal person? How long does an iPhone last before I need to charge it again? Keyword search totally falls apart here. It doesn't know that those two phrases mean the same thing. For that, you need to understand the meaning, the semantics, and that's where vector search comes in. Okay, so your retrieval system did its job. It pulled a whole set of potentially relevant documents. That's only half the battle, though. Now you have to rank them. Which one is actually the best answer? This is where our ranking toolkit comes into play. Now, at the heart of both modern retrieval and that first pass at ranking is vector search. We just saw why you need it, right? And this is basically how it works. It creates a vector, just a list of numbers, that represents the query's meaning. And it compares that to the vector for each document to find the closest matches. But to get even more precise, we can use a much more powerful and much more expensive technique. So while vector search looks at the query and documents separately, a cross-encoder re-ranker looks at them together at the same time. And by doing that, it can generate a way more accurate relevance score. The catch? It's really slow, so you can only use it on your top few candidates. But what happens when even the super powerful sense of relevance just isn't cutting it? Take a look at this query from the legal world. A standard model that was trained on a general internet would be completely lost here. It might see the words, but it would have absolutely no clue what they mean in this very specific legal context. And here's exactly why. To a normal model, regime might just mean a type of government. Material just means, important. But in law, these are terms of art. They have very precise definitions. If your vocabulary is this specific, your off-the-shelf relevance models are going to miss the nuance completely. And this is the point where your loss analysis might scream at you that it's time to build your own custom embeddings trained on your own data.
And a ranking isn't just about how relevant the text is. For a really great product, you have to think way beyond that. Think about Google search. It's not just relevance, it's PageRank, right? A measure of a site's authority. If you're building for an e-commerce site, price is a massive signal. For a video platform, popularity, views, likes, that's what matters. A truly great ranking function is going to combine many of these signals together.
All right, you've got a solid retrieval system, you've got a smart ranking function, you've made it to the final level. Now it's time to face let's call them the final bosses, the really complex system-level challenges of orchestration, cost, and product design. Your users, well, they're going to ask for really complicated stuff. They'll throw a multi-part question at you, like this one. They want cheap gifts, but then they go and specify a budget of $50 or more, which kind of contradicts cheap, doesn't it? A language model might just get totally confused trying to pass this whole messy request to a single search tool. So the solution is you have to take control. You use a technique called query fanout. Your system doesn't just pass that messy user query straight to your backend. No. Instead, it acts like a smart dispatcher, breaking it down into multiple, simpler, more targeted queries that your search engine can actually understand and handle well.
And don't be afraid to search more. There's this great strategy called supplementary retrieval. Basically, for those really complex or ambiguous questions, sometimes the best thing to do is just call a bunch of different backends. Your text search, your image search, your product database, whatever you've got. It just increases your odds of finding that golden nugget of information. When in doubt, search more.
Now, as your system gets more and more complex with all these fanouts and multiple backends, your costs can just skyrocket. This is where a really powerful technique called distillation comes in. See, a huge general-purpose model is often way overqualified for one specific task. With distillation, you can train a smaller, cheaper, and faster model to be just as good at that one particular job. But even after all of this, after you've optimized retrieval, ranking, orchestration, and cost, your system is still going to fail sometimes. It just will. These are stochastic systems, right? Perfection is impossible. So what's the last trick you have up your sleeve? You punt the problem to the product manager. I'm mostly kidding. But a great product is designed from the ground up to handle uncertainty. When the system is super confident it has the right answer, go ahead, show a rich, detailed, interactive UI. But when its confidence is low, it should gracefully degrade. Just back off, show something simple like a list of links, and let the human user make the final call. So, remember to be empirical. The path to quality isn't about finding some single magic bullet algorithm. It's an iterative loop. You baseline your system, you dig into the data to find out where it's failing, and then, and only then, do you apply one of these techniques from your toolkit. So you've got the tools now. The only question left is, what's the very first thing your data is telling you to fix?